Welcome. So we're going to review for curve sketching before we get started. All right, so number one, how can we find the relative maximum minimum values of a function? Take the first derivative, set the derivative equal to 0, and solve to find the critical points. Make a sign chart to determine if the function is increasing. If f prime of x goes from positive to negative, you have a relative maximum. If f prime of x goes from negative to positive, it's a relative minimum. Also check where f prime of x is undefined. So your critical points are where the first derivative is 0 or is undefined. And you can also use the second derivative test by substituting into f double prime of x your critical points. If f prime of x is less than 0, it's negative, it's a maximum. If double prime of x is greater than 0, it's a minimum. And we just saw that in the last podcast. How can we find absolute maximum minimum values of a function? That would be EVT. Right? So I did post a video from extreme value theorem, so if you did miss any of that lesson, I did put in your pot up. Check if function's continuous and differentiable on the interval. Those are requirements for extreme value theorem. Take the derivative, set it equal to 0 to find the critical points, plug in the critical points and the endpoints into the function. The largest value is the absolute maximum, the smallest value is the absolute minimum. How can we find the concavity of a function? Take the second derivative, set f double prime of x equal to 0 to find critical points, complete a sign chart. F of x is concave up if f double prime of x goes from negative to positive. F of x is concave down if f double prime of x goes from positive to negative. So where, and actually I don't like the way I said that. I actually gave you the inflection points. Let me just change that a little bit. And so f of x is concave up, or f double prime of x is positive, and f of x is concave down, where f double prime of x is negative. Right? And then inflection points occur where f double prime of x changes sign. How do we find the x-intercepts of a function? You set the function equal to 0 and solve. When will the function have a vertical asymptote? When the limit as x approaches some value approaches negative infinity or infinity. And how can limits be used to find horizontal asymptotes? Let's scroll up just a little bit. The limit as x approaches positive or negative infinity, if that is a finite value, then that finite value is a horizontal asymptote. So a little review there. And this is concepts that have expanded the entire quarter. This is in your notes. All right, so these are the steps. Now we're going to take everything we learned and we're going to put it together to do some curve sketching. In this video, I'm just doing a review. I'm going to go over the steps. I'm going to start a problem because I've already recorded the end of that problem. So I figured rather than retape what I've already done, I'm just going to tape to where I get to where that next video picks up. All right, so first, determine the x and y intercepts of f of x. All right, to determine the x-intercept, you set your function equal to 0. To determine the y-intercept, you set x equal to 0. Find the vertical and horizontal asymptotes, if there are any. Functions that have vertical asymptotes include rational functions sometimes, and some trig functions, and log functions. Graphs that have horizontal asymptotes include exponential functions, some rational functions, often rational functions, and that's it. All right, so find the vertical and horizontal asymptotes, if any, for f of x, the domain and range and end behavior. Taking the limit of a function as x approaches positive or negative infinity can be used to find the horizontal asymptotes. Horizontal asymptotes equals the limit if f of x goes to a constant as x approaches positive infinity or negative infinity. determine the first and second derivatives of the function, complete a sign analysis of the first derivative to determine the intervals where the function is increasing and or decreasing, determine any relative minimum or maximum values, and you're looking for, by the way, add in anything that's written in. There's not much, but add in those little bits of pieces of information that are written down. Write those into your notes. So you can either look for changes in sign for the first derivative using the sign chart, or you can use the second derivative test. With the second derivative test, you plug in the critical points into the second derivative. If it's positive, it's a relative min. If it's negative, it's a relative max. Use the second derivative to complete a sign analysis of f double prime of x to determine concavity. Using f double prime of x, find any points of inflection. It's where the second derivative changes signs. And complete a careful sketch of the function that supports all of the above features. An additional feature to graph the function accurately, determine the symmetry. There are three types of symmetrical functions: even functions, odd functions, periodic functions. Even functions occur when f of x equals f negative x and are symmetric about the y-axis, like cosine graphs, and y equals x squared, and y equals x to the fourth. Odd functions like sine and odd power graphs, like f of x equals x cubed and x to the fifth, occur when f of x equals negative f of x. So if you plug in a negative x and you get the same thing, it's an even function. If you plug in a negative x and you get the opposite, complete opposite, then it's symmetric about the origin. And then periodic functions occur. So periodic functions are things like sine and cosine. And when we have those kinds of graphs, we're just going to graph one period. Okay, vertical asymptotes. The vertical line x equals c is a vertical asymptote of the graph of f of x if, as x approaches c from the left, f of x approaches positive infinity or negative infinity. As x approaches c from the right, the limit as x approaches c from the right of f of x is positive infinity or negative infinity. Right? So if it grows without bounds as we approach some finite value, then that would be a vertical asymptote. Horizontal asymptotes, the horizontal line y equals b is a horizontal asymptote of the graph of f of x if the limit as x approaches negative infinity of f of x, or the limit as x approaches positive infinity of f of x is some finite value. Okay, and that finite value is the horizontal asymptote. Right? Should I erase this? Sure. I'll erase this part and go over it with you. On this problem, it switches over to the next video. So that's why it wasn't erased already. X and y intercepts, all right? So to find the x-intercept, you're going to set the function equal to 0. So 0 equals x cubed minus 3x squared plus 4. All right, this is not a pretty factoring one. Factor by grouping isn't going to work here. All right, so you can use a rational root test to limit your possible solutions. All right, so rational root test, possible solutions are the factors of the coefficient, which in this case is 4, divided by, not coefficient, excuse me, constant. Factors of the constant value, which is still 4. That's what I meant to say. Divided by factors of the leading coefficient. I'm going to put LC for leading coefficient. In this case, it's 1. All right, so your only possible solutions are plus or minus 1, plus or minus 2, and plus or minus 4, the factors of 4. All right, and then we've narrowed it down to 6 values. You try one out using synthetic division. All right, so you just use the coefficients. Man, that looks just terrible, doesn't it? Let me try over here. All right, so let's try 1. So 1, 3, negative 3. There's no x term, 4. So 1 times 1 is 1. Add those, that's negative 2. Times 1 is negative 2. Add, you get negative 2. And no, 1 is not the right answer. All right, so let's try 2. So I looked at what it was. 1, negative 3, 0, 4. We're down the 1, got 2, add, get negative 1, multiply, get negative 2, add, negative 2. Negative 2 times 2 is negative 4, add, we get 0. So that's 1. And then we have 0 equals x squared minus x minus 2. This will factor to x minus 2, x plus 1. So another 2 and a negative 1. So those are the x-intercepts. Right? So 2, 0, and negative 1, 0. And the y-intercept is easy. So these are x-intercepts. The y-intercept, of course, is 0, 4. What you get when you plug in 0 for x. There are no vertical and horizontal asymptotes. Right? This is a polynomial function. Right? So vertical and horizontal asymptotes, there are none. The domain is all real numbers, right? For a polynomial, any polynomial function. And the range is all real numbers because this is an odd polynomial function, right? It's S-shaped. Remember that from Algebra 2? It's S-shaped. So the end behavior, the function is going to approach, and we have a positive leading coefficient, right? So it's an odd degree, positive leading coefficient. This should be very familiar from Algebra 2. So f of x approaches negative infinity as x approaches negative infinity. F of x approaches infinity as x approaches infinity. Right? Grows and decreases together. Determine the first and second derivatives of the function, and then we'll set those equal to 0. Right, so we have the function written up above there. So y prime or dy dx is equal to 3x squared minus 6x. We'll set that equal to 0. This is to find the critical points for the first derivative. 0 equals 3x squared minus 6x. We can factor out a 3x. We'll have an x minus 2. So x equals 0 and x equals 2 are the critical points for the first derivative. All right, that's fine. And there's no place where the first derivative is undefined. Let's find the second derivative. So we have y double prime. That would be 6x minus 6. Set that equal to 0. So 0 equals 6x minus 6. 6 equals 6x, so x is 1. This is the critical point for the second derivative. Right? And this is close to where I think maybe the video starts here, the next video. I'll finish up this slide, and it might be that you see the same slide twice, but that's all right. Maybe I say something different. I don't always say the same things. Yeah, it's basically the same, but not completely the same. All right, complete a sign analysis of f prime of x to determine the intervals where the function is increasing and decreasing. So we have our critical values of 0, 2, so those could be possible extrema. I do have the sign chart already up here. Right, so our two critical points were 0 and 2. If we plug in something less than 0, like negative 1, into the derivative, which is not on this page anymore, 3x squared minus 6x. Right, if I plug in negative 1, we have 3 times negative 1 squared minus 6 times negative 1. That would be 3 plus 1. That was 9. Right, so that's a positive value. If we plug in something in between the two critical points, like 1, we have 3 times 1 squared minus 6 times 1. That's going to be negative 3. That's a negative value. I'll even write that in there. 9 and negative 3. And then if we plug in something greater than 2, like 3, we have 3 times 3 squared minus 6 times 3. 3 times 3 squared is 27 minus 18. That'd be 9. So that would be a positive value. Oh, I have it written down over here. I didn't even notice. I didn't even bother to look. So based off of our sign chart, we can see that f of x is increasing from negative infinity to 0 and 2 to infinity, because f prime of x is greater than 0. F of x is decreasing from 0 to 2 because f prime of x is less than 0. Determine relative max and min values, right? So we can use the first derivative test or we can use the second derivative test, right? So using the first derivative test, let's see, give myself a little bit more space. All right, so using the first derivative test, right, so x equals 0, or let me just put it, make my sentence a little bit better. There's a relative max at x equals 0 because f prime of x changes sign from positive to negative. At x equals 0, there is a relative minimum at x equals 2 because f prime of x changes. Need a little more space. Oh, no, can't find my, can I reach it? There you go. Changes, that's a G, not a Q. Changes sign from, what was this? Relative minimum, okay, from negative to positive at x equals 2. That would be using the first derivative test. Using the second derivative test, plug in our values into the second derivative. The second derivative, I don't know what the first derivative is because I can't see it anymore. It's like 6x minus 6. My screen's a little off, so I can't seem to scroll from up over there. What was it? It was on the other page. 6x minus 6. There's our function, and there's our derivative, 6x minus 6. All right, so second derivative test. Oops, scroll down again. So f double prime of 0 would be 6 times 0 minus 6. So that's negative, since f double prime of 0 is less than 0, x equals 0. There's a relative max at x equals 0. F double prime of 2 would be 6 times 2 minus 6. That would be 6, since f double prime of 2 is greater than 0. There is a relative min at x equals 2. So here are two different ways, first derivative test and second derivative test, that we can justify the extreme values. Okay. Oh, and feel free to, you have this in your notes, to stop the tape, pause it, and so you can take notes. Okay. And I think the next slide, no, maybe not. Maybe it's, oh, it's somewhere over here. Yeah, I think it's right over here. Oh, it's on this one. All right, so it's the next problem that is on the tape. I'll leave this one up here because there's not much written in here. So use the second derivative test to complete a sign analysis of f double prime of x to determine concavity. All right, so we had already, I did this on the other page. We set f double prime of x or y double prime equal to 0 and solve for x, so x was 1. Right? And you can plug in values on either side of 1, like 0 and 2. If you plug in 0, you get -6. If you plug in 2, you get 6. Right? Those were the values we set on the other page. So f of x is concave down from -infinity to 1 because that little upside down triangle of dots there means because f double prime is less than 0, f of x is concave up on 1 infinity because f double prime of x is 0. There's an inflection point at x equals 1 because the second derivative changes sign from negative to positive. There's an inflection point anytime that second derivative changes sign. Okay? And then to find the y value, just plug it into the original function. So if we plug in 1 into x cubed minus 3x squared plus 4, we get 2. So 1, 2 is the inflection point. On the AP exam, it's not enough to state that a value is a critical value or draw the sign chart. An explanation must accompany your answer and chart. Right? So, do the sign chart. Right? Use whatever you need to help you remember, but make sure you justify. Concavity test can be summed up with the following pictures. While this is humorous and hopefully a helpful way to remember concavity, please understand this is never to be used as a justification on any test. Right? So positive, he's got positive eyes, concave up. He's got negative, his eyes are all closed, concave down. Right? Because when if the second derivative is positive, the graph's concave up. When the second derivative is negative, the graph's concave down. But while helpful to help you remember stuff, not helpful in terms of justifying anything on the AP test. Right? Justify in words. Just use that to help you out. All right. I think the I think this one is on the next video. So I'm going to stop the tape right here. All right. And thanks for watching this part, and then I'm going to pick up on the next video. Bye for now.